seminar speaker, Dr. Mark Chance, who's a professor in the Department of Physiology and Biophysics here at Case Western Reserve University. Now, at dinner last night, Mark asked me, keep it short, 25 seconds, no more, no less. And I was going to do that, but we still have time to set up his presentation, so I get to go a little bit over to talk a little bit about Mark. Mark, I'll go through a little bit of his pedigree. He received his PhD at the University of Pennsylvania, went into industry for a little bit, and did a postdoc at Bell Laboratories, and then went on to academia and developed an outstanding career during the time where he's published well over 100 papers in very prestigious journals, Science, Nature, and so forth. He started out at Georgetown University and then moved up to the Bronx at the Albert Einstein College of Medicine. And I think what's fascinating is that his time at the Bronx, he never developed an accent, a New York accent. Or maybe he did, but he just hides it very well. But I think the reason he never developed an accent because he was in the laboratory in his office all the time, developing just a dynamic research program. He rapidly moved through the ranks from assistant to associate to full professor, working in two distinct areas, both in structural biology as well as integrating proteomics and mass spec. In 2005, based upon all of his accomplishments, he was recruited here to develop a Center for Center for Proteomics, and he's been very dynamic in that. In the past 2.5 years since he's been here, he's accomplished many of his goals and has established this Center for Proteomics as one of the best in the country. He also wears many hats. Not only is he the director for the Center of Proteomics, but he's also the director for Synchrotron Biosciences, and he's working extensively right now to help develop some new initiatives in systems biology. So Mark, it's great to have you here. We look forward to hearing your talks and what I consider to be really a new frontier in pharmacology, using mass spec and proteomics to develop diagnostic and prognostic tools in the treatment and diagnosis of disease.
Good morning. Thanks to Vida and Chris for organizing this symposium. It's a tremendous lineup for today. I feel very privileged to be included. I've been here at Case for 2.5 years, and the reason I came is both a combination of terrific basic science, where I could continue my structural biology program and that of my colleagues, but also the opportunity to develop a more clinical and translational focus in the area of proteomics and systems biology. And the medical school is making tremendous advances in its clinical research portfolio, and I'd like to talk about just a very small fraction of an effort which involves many, many faculty in many areas. And it's just simply titled Urine Biomarkers for Diabetic Complications. And we developed an interest in diabetes a number of years ago when the NIH developed some RFAs to use proteomics to try to examine what's going on in the disease. And much of that effort was directed towards diagnosing diabetes. We took a different track entirely. We thought that the important advance needed to relate to how do we distinguish which patients are going to develop complications and who should benefit the most from specific therapy. And at the end of the talk, that will raise again the question of personalized medicine and how do we get from here to there. So the statistics are grim. 20 million people in the US have type 1 or type 2 diabetes. This is in excess worldwide, excess of 100 million people with the aging of the population and the negative lifestyle changes we're all familiar with. These numbers are growing to epidemic proportions. We are in an era of management of diabetes that's far more effective than has been in the past, certainly. So what does that mean? Chairman of endocrinology at Einstein said rather grimly, well, unlike cancer, diabetes is a great disease for physicians because they're living a long time and we get to see them and treat them in a chronic sense. And so eventually, many patients suffer from complications such as end-stage renal disease, coronary artery disease, and so these particular conditions are exploding along with diabetes. For example, diabetes is the leading cause of kidney failure. Almost half of kidney failures in 2002. So that's 60,000 patients with end-stage renal disease are dying yearly in the United States. Coronary artery disease is the leading cause of mortality in the US, and with diabetes, your risk is increased dramatically. So a number of observational studies have defined this problem a little more quantitatively. I want to show you just a couple. This is from the Pittsburgh EDIC study of type 1 diabetics. And what they did is they looked at the incidence of various complications for patients as they progressed. So if you were diagnosed 30 years ago in the 50s, you had a 30% chance of renal failure after that time. The good news was if you were diagnosed more recently, the incidence went down with significance. Same for those who were diagnosed 25 years ago, had about a 25% incidence of end-stage renal disease, but things are getting better if you were diagnosed more recently. That shows that management has been effective for the disease. 20 years ago, even better. However, the incidence is still unacceptable to the patient. Again, 60,000 deaths as recently as 2002. Now, over on the right, you see some similar statistics on cardiovascular events for patients diagnosed 30 years ago, or excuse me, patients who had a diagnosis at an interval of 30 years and were sampled after 30, so long time ago, more recently, and very recently. The story's very different here. If you've been diagnosed more recently, your incidence is in fact going up if you have diabetes. Okay? So we are not making any progress for type 1 diabetics in terms of their cardiovascular events, just the opposite. More recent diabetes control and complications trial tried to look at the effect for type 1 diabetics when on conventional therapy and intensive therapy. And intensive therapy is just that. Sampling your glucose 4 times a day, insulin 4 times a day. It's a very difficult procedure to maintain. It brings your markers for your blood glucose down, though, to that of normals, as if you didn't have diabetes. So if you look at years from study entry on conventional therapy, where you take insulin, here's the incidence, cumulative incidence of a sum of various cardiovascular related events. But if you're on intensive therapy, the risk reduction is 57%. That's very impressive. And DCCT has gone on to show once the patients go off therapy, the benefit is maintained over time. So there's really something significant here. What's the problem? Intensive therapy has risk. Hypoglycemia can cause coma. Those who suffer any kind of incident while driving have a car accident and often die. So we need to be very careful about who we recommend for intensive therapy. Who do we give it to? Can we judge who is at greatest risk for developing these complications so we can segregate our patients into those who receive conventional and those who receive intensive therapy? Biomarkers for looking at the disease progression are essential to making these kind of decisions. And physicians tell me anecdotally that they have some patients who have relatively uncontrolled glucose levels, and they seem to do not suffer complications, while others seem to deteriorate rapidly. What are the genetic and other factors that are involved? Well, the biomarkers of diabetes complications that we have some limitations. And basically, albumin excretion in the urine is really the gold standard for a diabetic nephropathy, kidney damage, and coronary artery disease. The problem is the measurements are somewhat nonlinear, as they call it in technical terms, over time. Just an example, here's the Jocelyn study, patients with about 400 patients with so-called microalbuminuria, followed up 6 years later. A number of them went into remission with respect to this biomarker. A number progressed. the biomarker was not really a reliable predictor, even though it's the gold standard. Many studies have shown this. We need better markers as to how the patients are progressing. So albuminuria implies that there's a change in the protein composition of the urine, obviously. So what proteins get into urine, and is there some logical conclusions we can make about what we might be able to see? So the sources of urinary proteins include soluble proteins. So here's your glomerulus. There's an artery coming in, and the solutes are filtered. Here's the loop of Henle in the proximal tubule, and proteins that leak through the glomerulus often get reabsorbed in this loop of Henle. Some of them get back into the circulation, and some get digested. There's also epithelial cell secretion of soluble proteins that can come into the loop, and there's shedding of cells and exosome secretion, and all these can lead to the ureter, to the bladder, and so on. Now, the urogenital complications that can occur involve changes in the glomerular filtration rate. That'll change the distribution of proteins that break through that glomerular wall. You can have defects in proximal tube resorption for proteins that are supposed to be recaptured, and other defects in lysosomal processing and changes in extracellular matrix proteins. And these are not well studied or not well understood, but they're certainly understood to some level. In the hyperglycemic attack that occurs to these tissues in diabetes, various of these defects do occur. How they affect what the protein composition of the urine is pretty much completely unknown. So we had some familiarity with a rat model of diabetic complications. It's a good model for type 1 diabetic complications in that the rats at initiation are treated with a drug called streptozotocin. It destroys their insulin-secreting cells in the pancreas, and so they immediately become hyperglycemic and suffer the effects of hyperglycemia as they progress. And in the progression of this disease, we have looked at some of the specific end organ alterations by a number of proteomics and microarray approaches, and followed the progression of disease with various physiological approaches with some of our collaborators. And I won't talk about a lot of that aspect of the work today. It's been mostly done by Elizabeth Johannes in my laboratory. She had a very nice paper in molecular and cellular proteomics a few weeks ago. But they defined pathophysiological changes in organs like bladder and corpora that are associated with disease progression. And they showed that at these early times, at 1 or 2 months after administration of STZ, there's minimal pathophysiology, as the physiological studies show. That is to say, this is a pre-complications phase that we might consider focusing on if we want to develop biomarkers for the disease. By this time, okay, you're suffering physiological damage, and it's a little later than you would want to consider going to intensive therapy or trying to administer treatments. So we decided to look in the urine of rats in this rat model and focus on this early phase of 1 or 2 months to see what biomarkers were progressing in the urine, if any. And we did a study with 27 rats where we looked at their urine control and STZ-treated groups at 3 days, 10 days, 1 month, and 2 months. And only really at 2 months is there any indication of any kind of pathophysiology going on. So even at this stage of the study I'm going to show you, the rats are pretty healthy, other than having too much glucose in their urine, as well as their circulation. So urine is a terrible matrix for doing proteomics. It's full of salt, it's very dilute, people avoid it like the plague. So we needed to develop a method for sampling urine that was reproducible, that dealt with the issues that protein concentrations tend to change with urinary output during the day, for different patients, et cetera. A lot of difficulties. To summarize, and we decided, we'll use simple SDS page gels to sort of as a quality control to view samples and look at the reproducibility of the samples. So basically it involved an ultrafiltration and wash protocol and making a decision that all samples would be normalized for protein load. So everything I'm going to show you, every sample from every rat or patient that we'll see by the end of the study, it's all normalized to the same total amount of protein. Now, as we did this QC with the gels, we saw, wow, this is very different. The normal gel pattern has these low molecular weight proteins you'd expect from breaking through the glomerulus, and has albumin, of course, which is everywhere. But then in the diabetic, and this is just a sample which has a protease cocktail put in to show that urine really doesn't suffer any proteolytic digestion, the protein processing pattern was changing dramatically this is a 1-month diabetic sample. And this was very reproducible. That is, for every rat, if we run a 1D gel band, their protein pattern is completely characteristic of whether they're normal, 1 month, or 2 month. So we decided to ID some of these proteins, and they were some of the usual suspects you'd expect for a serum filtrate. But clearly there's a dramatic change in their distribution, likely due to changes in glomerular filtration rate. So let me just make a caveat, and it applies to animal models in general. This is just a model of the human disease, and one way in this model deviates significantly from the human disease is the glomerular filtration rate goes down in these rats at these early times, as opposed to going up in humans. So as we know how to do, we digested proteins into peptides, and we ran them out on chromatograms with reverse phase chromatography. And here's a 3-day STZ treated, 1 month STZ treated, and 2 month. And there are really dramatic changes in the processing pattern. You see this peptide species is way high in 3 days, tends to disappear. These species are relatively more constant. This one comes up and down. Very nice, very reproducible patterns. But I want to remind you that because each of these fractions gets separated by reverse phase chromatography and then goes into the mass spectrometer, each little peak you're looking at, for instance, the one at 78 minutes, might contain 30 to 100 distinguishable peptide species that we can individually quantitate and monitor. So in fact, there are thousands of entities we can compare across this chromatogram. And as you'll see in a minute, this is somewhat of a biostatistical and bioinformatics challenge to extract what are the statistically significant and reproducible differences here. So this is a typical workflow for an expression analysis. This has no labeling in it of any kind. We need to process this raw data, which has intensities and samples. And this is again that raw data. This is the 27 samples. This is a heat map where the green is a high intensity and the red is the low intensity and the white is somewhat in between. So we have to go through each of these and generate masses in terms of peak lists. We have to assign and integrate those to chromatographic peaks. And then we have to put a peptide sequence assignment on it by our tandem mass spectrometry methods. And that gets assembled into this sample versus mass and intensity kind of matrix here. And this is the raw data that we get. Now, you've probably all seen heat maps from microarray data. And the one difference that you see between here and there is I have a lot of holes. Okay? I have a lot of places where I didn't get an intensity. And it's a serious statistical problem. I cannot properly analyze this in this fashion. And so biostatisticians have come up with some rather clever ways to impute the intensity in these regions, and that imputation is shown here. And then I have to normalize that data. So again, in that data QC, I have to filter my poor quality chromatographic peaks. I have to replace missing values. And then I have to normalize that to a more reasonable distribution. And then I have something I can subject to statistical analysis. This is a blow-up of a heat map with some diabetes versus normal samples. And now you can see that there's a very high intensity of a particular chromatographic peak here assigned to a certain mass compared to that in control. And this is the data that we can do ANOVA, principal component analysis, false discovery rate analysis, all the things we need to do to properly process the data. So for this particular experiment, there were about 3,000 peptide entities that we could survey. Over 800 we could sequence and say this was assigned to a particular protein. 500 were of quality that we thought was reasonable. And of these 500 peptides, the statistics said 64 had reasonable p-values after false discovery rate for what we call interaction. So remember, this study has intervals of both time and treatment. And so we thought that was a rather good study design in that if we study the multiple variables together, we will find the peptides that not only are different, but progress as a function of disease. And we think good biomarkers should stage the disease as much as possible. And these peptides represent about 30 different proteins that, again, showed progression upon treatment. So what are they? What are some of the specific biomarker candidates? Well, these are a couple which actually were relatively satisfying and sort of gave us confidence that we understood what was going on with respect to the physiology. This is the major urinary protein precursor in rats. It's the odorant protein. I'd mentioned these were all male rats, so they had a substantial odorant that they would put around their cages. And this is that protein. These are the control data, and the MUP goes up a little bit. And then in the treatment, it goes down substantially. Same for urinary protein precursor 2. And we think this is simply reflective of the drop in glomerular filtration rate for the rats during this time period. Okay. More interesting was pro-alpha collagen 2, which we thought was reflective of biological changes going on in the kidneys of the rats. Now, for this STZ rat model, a number of studies have shown that collagen gene expression is increased as a function of the glycemic attack that the kidney is undergoing. So we're seeing increases in the specific pro-alpha form of collagen, highly significant as a function of treatment and time. And we think that reflects not only increased expression in the kidney as a function of progression of disease, but also defects in processing, because this is a pro-alpha peptide that we're detecting. So we wondered, could we go back and validate this peptide and do absolute quantitation in order to understand the actual levels in the individual rat samples? And we used a biomarker validation strategy called isotope dilution tandem mass spectrometry. I'll save all the details of this when I speak at the American Society for Mass Spectrometry later next month. I don't think you're interested in it. But basically, it relies on making an internal standard peptide and spiking that into your samples and comparing the intensity of the internal standard versus the analyte of interest and defining the absolute concentration of the analyte. Some of the advantages of this method are that it's sensitive. It's at the level of ELISA sensitivity. It's extraordinarily specific. You only measure the analyte you're interested in, and you get an absolute measurement of the concentration of the species. So here's the pro-alpha 2 collagen peptide sequence that we chose. This is the method development, generation of the standard curve, where you're looking at intensity versus number of femtomoles per microliter. And this shows a particular extraction for 250 attomoles of this peptide, which has a signal-to-noise of about 300. So you really can see this pretty easily in a urine matrix. And so when we go back and measure the absolute concentration of this peptide in the rat urine samples, I think we see a couple of points. One is that it goes up. Well, we already measured that, right? We had a good idea, but now we know the absolute level. But I think some other things are interesting. One is the controls and the 3-day diabetics and the 1-month controls, they're all in a very tight concentration range for this peptide. Those numbers are just indistinguishable. The 2-month control shows the time effect that we do observe. I didn't talk about that much, but there is a time effect we can detect. And the diabetics are up at 1 month and 2 months, but not all rats are equal. Some animals are more equal than others, it's been said at one time. And we think this reflects, I don't have the data today to prove it to you, but this reflects the individual progression of these animals, at least with respect to this biomarker, and perhaps with respect to what's happening in their disease. So perhaps this is the dawn of personalized veterinary medicine at this point in the talk. So the rat model, I think we were very satisfied with. It allowed us to develop the methods to extract the urine samples properly, detect the proteins in a statistically significant way, and discover, I showed one biomarker that has some biological relevance with respect to the known physiology of this animal model. But really the money shot is to get this into human urine, and we initially worked with the cacti group at the Barbara Davis Center in Denver, who are conducting the coronary artery calcification in type 1 diabetes study, and got some samples from them and tried to follow a similar pathway to see what we would get. So the human urine protocol was optimized. 4 mils of human urine turns out to be a pretty ideal amount. That's important with respect to a number of national biobanks that exist. We initially looked at 3 controls, 3 diabetics, again these are type 1, and 3 diabetics who'd progressed to macroalbuminuria, and these were age matched within this range, but multiple sexes. So we said, well, let's do the 1D gels. Here are the controls, here are the diabetics, here's the samples with albuminuria, a lot of albumin in the urine, no big surprise. But we also saw the kind of changes that we saw in the animal model. Here's a band which corresponds to uromodulin in controls. It's going down in the diabetics, and even potentially changing further in the albuminuria samples, though the albumin tends to spill over in the 1D gel. But not inconsistent with what we'd seen in the rat study. So we went on to do LCMS of the peptides. Here's an example of a single run of the albuminuric, the diabetic, the control. I have to I forgot to put circles on here to remind me what to show you, which is bad form for me. Now, of course, I can't find them. They're peptides which change substantially. What can I say? Let me go to the summary statistics. Here we did a little different method with some little more significance. We detected, in fact, over 7,500 separate peptide entities in these samples. assigned a sequence to over 1,000, and were able to analyze 826 peptides that passed a QC filter and were analyzed by ANOVA. Here's the bottom line. The controls aren't that different than the diabetics, and that is really good from my standpoint. There were only 27 peptides that were significantly different between those groups out of the 826 that were examined. For diabetes versus albuminuric, nearly 400 peptides are changing. Control versus albuminuric, also 400 peptides are changing. No surprise, most of these are in the same group. Now, this is the part I hate. Well, it's not yet, but it's coming. If we do principal component analysis, we can see with only 2 principal components, we get complete separation of the groups. The control is very like the diabetics, and the albuminuric is way over here on the side. It was just a very clean study from statistical standpoint. And we decided to do quantization of extracellular matrix-related protein. Now, this borders on the talks I've been to where it's target XZ47.5, and I apologize for that part. But the tech transfer office won't let me tell you what that is yet, but give them a couple of weeks. Just think extracellular matrix-related protein in the context of the rest of the talk, and maybe you can figure it out. But here's the standard curve for the human variant of this protein, and here are the controls, the diabetics, and the albuminuric, again reflecting the substantial distribution we see in the diseased, progressed patients. So I'd like to give you the conclusion and then a couple of comments. We're satisfied we've developed an analytical protocol that accommodates the low concentration of proteins in urine and can be conducted with volumes that are consistent with national diabetes studies, which frankly have thousands of samples banked over the last 10 years, and they haven't figured out yet what to do with it. I hope I can convince them what to do with it very soon. We saw very significant differences in the rat model across treatment and time. And the pilot study shows differences in the human data that are very consistent with the rat model, and we have validated some of these markers in this. I shouldn't use the term validated unless I've gone to a separate cohort of samples probably, but we have confirmed the absolute concentration of some of those markers in our sample. So we're working with the Barbara Davis group to define predictors specifically of coronary artery disease with a set of samples, and we can do that without discovery now because we have specific candidates we can bring directly into the validation assay by this mass spec-based analytical method, which is quite rapid. And I want to close by with another point, and that relates to the future of diagnostics, in my view. I had the privilege of visiting with Jeff Immelt, the chairman of GE, several months ago, where he had a town meeting with a number of his customers, and the Proteomic Center is a very good customer of GE. He showed some of the strategic plans for GE over the next 5 years, and they had a number of areas they were targeting. And one of them was called demographics. And that had 2 elements. One was in the third world, there's going to be increased consumption of material goods, and so those folks need loans so they can buy TVs. So, okay, that's a GE finance part. And the second part of demographics related to healthcare and the aging of the population. And his numbers went as follows. And we're spending about 14 cents, maybe 15 cents of our dollars in gross domestic product on healthcare right now. His team is fairly sure that's going to go to 20 cents on the dollar. Within that dollar that we spend, the vast majority is on treatment, maybe 70 cents, with 20 cents on diagnostics and 10 cents on administration, give or take. He believes that's going to go to more equal spending on diagnostics compared to treatment. And that means we need diagnostics to gauge who to treat and when to treat them. And I came out of that thinking, I'm glad my money is on the same number on the table as Jeff Immelt, because as that roulette wheel spins, that's probably a decent place to be. We'll see if he's right. I want to thank the people who really did the work. Danny Schlatzer is the leader of our LCMS Proteomics Discovery Group. Rob Ewing is a new faculty member in the Proteomics Center who does the bioinformatics analysis. Johnny Dezard is an assistant professor in epidemiology and biostatistics who's developed some of the novel biostatistical methods for proteomics that we've had to develop and use for this project. Elizabeth Johannes has done the systems biology work in diabetic organs of rat. Katie Lundberg did a lot of the LCMS quantitation analysis, and other members of the Center for Proteomics team were essential. George Christ is our longtime collaborator at Wake Forest University. He and I were buddies in the Bronx back in the day. And recently we've been working with the Barbara Davis Center for Childhood Diabetes, which is headed by Marion Ruers. And I also want to thank the NIDDK and thank you for your attention.
Questions for Mark?
Mark, that was very fascinating. I was wondering to what extent do urinary protein changes affect serum protein changes, and to what extent do they affect kidney-specific changes?
So both of those are in there, right? Because you're a serum filtrate, so it's going to be a combination of those. What changes in the serum, and then how the kidney handles that, and then what expression changes are occurring in the kidney that may, lead to things happening in the glomerulus. But it's not very well understood. And I have to admit, we're going to have some difficulties teasing out, what we see in the urine, where we have maybe 4 or 5 different processes that are putting proteins in or taking them out, depending on the disease progression. So it's not going to be simple.
Mark, you're pointing to me, right? Yeah. So on the human data slide, you showed significant variation on the 3 patients, I guess, that were tested at 2 months. There was a red, a blue, and a green dot, and they splayed up and down from low to very high. How are you going to resolve that to make this into a useful biomarker? Do you think statistics are going to further cull us? No. The only way to do this is, in my view, is because studies like the cacti and have samples that go back a number of years, starting when the patients had no albuminuria and no complications. Okay, so we need to design a study now where we select carefully a set of patients who were healthy and stayed healthy through 5 years, where we have urine samples every year, patients who were diabetic and did not develop complications, patients who were diabetic and did develop albuminuria, renal disease, or cardiac event, or had some significant change in their echocardiogram, which is another one of the physiological variables that we monitor. So you've identified the problem in this data is I don't know what these, I don't know the progression history here, but the biobanks absolutely exist to ask that question in a very focused and even a double-blinded kind of way if we want to get to that point.
Do you see, I have one specific question. Do you see changes in RBP, regional binding protein?
I don't know.
Maybe one of proteins worth to look at.
Okay, it's a protein worth looking at if it.
And the second, if you think about utilization of the diagnostic method, do you envision that one day there will be one or two proteins you will be looking at, or 1, 2 peptides, rather than this massive approach? Because that kind of will limit which center can do the analysis.
I think you exactly want to focus on a set of proteins that are specific for the particular complication that is going on, and get it down to an ELISA assay that could be done in the doctor's office, or who knows, even at home. But right now, as a research tool, the mass spectrometry I think is sufficient. But I don't want to do discovery and look for 7,000 peptides every time I dip into the Barbara Davis biobank. I want to have very specific candidates, more like, this many, to carry forward into a detailed study of more like 100 patients.
Mark, one question I have
is, do you predict there's going to be massive differences between type 1 and type 2 diabetes growth?
Oh, thank you. I forgot about type 2 diabetes. So type 2 diabetics develop many of the similar complications as type 1 diabetics, and the markers just have not been studied. So there are going to be some in common. There are going to be some that are specific, and there's also, we're starting a study of sleep apnea, diabetes, and obesity, which obviously is a major strength here at Case with Susan Redline, where we can try to, again, tease out some of these different pathways of pathophysiology that are involved in this cluster of obesity, type 1 diabetes, and complications that result.
If there are no more further questions, let's thank Mark again.